Part of lecture 7. Um, I'm sorry, it took me a couple of days because I was really down and I could not talk because of cold and cough. So as soon as I got okay, I'm doing this. Anyway, the last part of this lecture is on tooling. Um, I would say that tooling is as important as the composite fabrication processes and materials itself. And that is because tooling costs are probably controlling many the composite part costs because each uh, part has to kind of draw a part of the tooling cost into its final cost. And many times, especially large composite parts, the tooling costs can be in the millions of dollars. So you can see that if a part costs $10,000, part of that $10,000 is due to the cost of the tooling itself. So we will be talking about that in the next few slides. So what is composite tooling? Composite tooling is the uh, female part for forming the male part, and many times uh, the newer platforms, they need to be made with brand new tooling, and the tooling has needs from specific for specific properties. And that's because many of the primary components nowadays for these new platforms like the 787, 380, and things like that, or even the new automotive uh, uh, platforms like the BMWs and the and Nissan. I mean, not the Nissan. I think now Honda is also trying to make cars uh, with composite parts, like um, the roof and things like that. They need to be made with parts, and even on the fuselage is not of the aircraft. It is not a straight circular part. It is a oval based component. So which means you need to have what is called a hat stiffened panel construction to make that part. Okay. So, and in this, I'm also going to introduce some of the newer types of materials that are used for making these tooling parts. And part of it also has something to do with a material that I developed about 16, 17 years ago. So, most of the tooling parts are made out of metal, and they are made from materials that are not traditional aluminum or stainless steel and things like that. Why? Because stainless steel and aluminum, they expand and contract a lot, whereas aluminum is like I believe it is 16 parts per million, whereas the composite part itself is going to be expanding and contracting at the rate of about 3 to 4. So there is a tremendous difference between the shrinkage and expansion of the two materials. So first of all, you have to account for the expansion of your tooling into your part dimensions. Second of all, that difference in shrinkage and expansion can cause the introduction of residual stresses into your part. And thirdly, there are going to be a lot of areas where you have hollow sections, you have non-traditional cross sections in the part itself. So your tooling has to take all that into account. So for these kinds of parts, we have come up with what are called water soluble tooling parts. And especially if you are going to be making a part that is going to be manufactured for say 10 years, 15 years, and so on, before you make the first part, you have to do prototyping. So before you make the production tooling, you have to make the initial prototype tooling. And nowadays, they make it out of water soluble tooling materials. So reusable tooling materials are either steel, aluminum, or Invar. Mostly Invar is the material of choice, but the problem with Invar is that it is extremely heavy. It is nickel based alloy. It's got the lowest shrinkage and expansion, like it can be, it is very close to that of the composite part itself. But the problem is that once you make the part, it is extremely hard for you to repair it. And as you well know, when you make the first part, that first part is never going to be accurate. So you have to modify the tooling, which means you have to cut it, you have to scratch it, or you may have to machine it again. And machining is going to be an extremely hard process for Invar. Steel and aluminum is okay, but the problem is that steel and aluminum expand and contract a lot. So the limitations are that these materials are inadequate, they are heavy, expensive, they have extremely long lead times. For example, if you have a $5 million tooling piece, it can take you about 6 months to make it before you get the final part. So if you are going to be making a prototype, it is not going to be an effective process. So what is required of the tool? It has to support the weight of the part. It has to maintain its structural integrity and dimensional stability. Suppose you are making hundreds and hundreds of parts. This tooling should not get damaged during the process, and you need to be able to sustain its handling loads. These materials are going to be, these tooling is going to be exposed to high temperatures and high pressures, and it has to accommodate the fabrication process. So what are the decisions? Whether it is male or female, which face of the part should be the tool surface, what kind of tooling materials are used, and what is the lifetime, what is the cost, what is the non-recurring cost of it, because you have to take the machinability into account, because as you know, aluminum is easier to machine than steel, which is then easier to machine than Invar. Then if it is an extremely big tooling, then you have to worry about the heat up and cool down times. So which means that you have to keep the tooling plus the part in the furnace for an extremely long time till it cools down completely. And so you have to take the thermal characteristics of the tooling materials into account. The other thing is that we worry about whether it is a hard tooling or the soft tooling. Soft tooling means, for example, if you have the turbine blade used in a wind turbine, okay, the inside is made from what is called a soft tooling. So which means that you have to replace that tooling part after every 100, maybe like every 100 cycles you have to maintain that. So with those kinds of materials, it is extremely difficult to maintain the tight tolerances. It might give you a low cost, but it is not easy because you have to remake that tooling piece all over again. The hard tooling is that it can last many cycles, but the cost can be extremely high. In your tooling design, you have to account for the thermal expansion and contraction, for example, and you have to account for the gel coat and the wetting part and things like that into the tooling design and the tooling dimensions. If, for example, the turbine blade used in the Gen X engine for GE, its clearances are of the order of microns. So you can see how critical the tooling can be in the part design and your part production. The tooling has a mind of its own. It will expand and contract at its own rate and not worry about the part. So there will be, as I said, there will be thermal stresses that will be introduced. And so which means that your part can contract and stick to the tooling. So which means it will be extremely difficult to extract that tool after the part is made. So which means that you may want to have a tooling that can be breakdown. So you can just release the tooling, but which means that it makes it extremely hard for you to make the tooling, extremely hard for you to design that into the tooling, and extremely hard for you to manufacture the part. Typically, the tolerances on the tooling are one-fourth the tolerances on the part. I mean, this is a very abstract rule of thumb, but it may not always be true. But that's the typical number that we work with. So here is an example. If your part requires the production of 5000 C channels, and there is a smaller C channel bonded to the inside flanges, and so your design number one in the 90-degree direction, um, it can be like, it is minus 0.2893 parts per million. But if you had design number two, your fiber angles are plus minus 25 degrees symmetric. Your CTE can be positive, and it can introduce a lot of complexity into your tooling design. So those are some of the issues that we have to really worry about. There are some typical types of tooling materials, like metals. So what you do is you machine the tooling, and then you do what is called so you have a fiberglass plating mandrel, and then you create what is called a splash tool, and then that splash tool is tipped inside the molding solution, and it deposits, and they call it electroless plating of nickel on top of that. So once the part is made, so this is how it looks like, and then you remove the plating mandrel, and so it gives you nice surface finish, but it's a very complicated way of making the tooling. So if you have a composite tooling, it will give you good match between the tooling CTE and part CTE. It is lightweight, it is lower cost, but it has limited life in comparison with metal tools. So those are some of the issues with uh, composite tooling. But composite tooling is typically like, if you want to make 1,000 parts and things like that, that is a very standard process for that. But metal tooling is still an accepted process, but it is an extremely expensive way of making tooling materials. So the fabrication of composite tooling, the different steps are listed here. I'm not going to go too much into detail about that. Basically, you are going to lay up the composite, You have a face sheet that is slightly different, and the bottom could be what is called an egg crate type of design, so that you reduce the weight even further. So, for example, um, if it is a huge uh, part like a wing structure or a ducting structure, so just imagine the weight of the tooling itself. Tooling, it can be in the tons weight. So the whole tooling has to be moved with a crane, a mechanized crane. And then after the part is laid up, you have to move the whole thing into the furnace. And then after the part is cured, you have to remove the whole thing. And then you have to have some way of removing the part from the tooling itself. So the lighter the tooling, the better. You have what are called metal coated composite tooling. So you can combine the advantages of metal and composite, but the method of fabricating is pretty complex, but it can be done. So you have the metal coating done by electrolytic or chemical plating, or you can also thermal spray the metal on the master, then you fabricate the composite tool over the metal surface. The other types of tooling are what are called segmented tools or mandrels to prevent trap tooling. You have elastomeric tooling, like for example, um, on the tooling for turbine blades for windmills, as I said to you earlier, or you can have areas where you have special pressure needs. So there are areas where you have no way of applying any kind of pressure. You need some kind of pressure in order for you to compress the composite layers. So by having this bladder, and you apply some kind of a gas inside that bladder, and it expands and just keeps the composite layers in place. Or you can also have what are called cowl plates. Cowl plates are very thin sheets of aluminum, and you are applying some kind of a vacuum bagging on the composite while it is being made. And what happens is that when you apply the vacuum, the cowl plate just comes and presses against the composite layers and applies uniform pressure over the part. And it will also maintain heat transfer similar to the tooling side. Or you may also have what are called ply locating templates. So I want to describe some of the things that we did about 16, 17 years ago. We came up with what are called washable tooling materials. And the advantage is that these materials have low thermal expansion, lightweight, and it does not have a polymer that will cross-link at the processing temperature. So after the part is made, you can easily wash it out and remove that. And unlike many of the types of tooling materials, washable tooling materials that are being used in the industry, like salt-based or sand-based and things like that, these are the ones that we developed were non-corrosive and environmentally friendly. So this is the process of making that water-soluble tooling. Basically, you mix a plaster and these tooling materials together, and then you mix it with water, make it into a kind of a pourable slurry. You pour that slurry into this tooling, into this mold, into this female mold, and then after that you dry it so that all the water is driven off, and then you get the mantle. And then you get the mantle, and then you coat it, and then you cover it so that the resin does not penetrate into the mantle itself. And then you lay up the composite on top of that, either by filament winding or something like that. And then you cure it inside the composite, either autoclave or non-autoclave it. And then you just wash out the material, and you end up with the final part without with the right kind of uh, right kind of uh, size and shape. Anyway, I have to stop here and start in the next section.